Here we go. Hello everyone and welcome to the result of the bonus round 2 from the 2021 SpaceChem technical demo. Now this is the gold rush and this features another pretty horrifying thing. Now let's start from the outputs because they look nicer. So this is a gold output because there is gold here. This is a silicon output and this is a 0 over 0. We have seen this in round 4, but what it means is this is basically a recycle for silicon. So you can just throw in silicon. It doesn't matter if you throw nothing or if you throw a billion atoms. This is already done. And then we have the ore vein, and you can see the preview looks a little bit strange. Oh, sorry. And it looks strange because it's this. By abusing pretty horribly the input format, you can input arbitrary large molecules. Like you could input a molecule big the whole reactor if you wanted. And for this challenge I decided to do this thing. Because yeah, I could input a big vertical molecule, but I think we have all seen enough polymers in our life. So I wanted to do something like this because you never see molecules this big horizontally, because you cannot output on a normal output something like this because you cannot rotate it, it's too big. And so this puzzle is about plucking these golds here and bringing them back to the output alpha. Now this puzzle is simple on purpose. Like a real puzzle of this kind would place these golds randomly, either randomly on the last row or randomly throughout, and will make your life a little bit harder. But I decided to make it fixed, so you could code the whole thing into the Waldos if you wanted, and we could see something different than the sensor checking things. Just one note on the metric. This is cycles, and basically you cannot use the tunnels. I put them in because I am not a good player and I could not solve this just with the bonders, and I needed this to help me. So I put them in and then gave them a massive penalty, so that even people like me can solve this puzzle if they use these bonders. So let's just start. We start with Astron Nelson that does this thing. So blue picks up, drops it here, and then it will use this bonder pair to strip off a strip, bring this back, and then red will lob off 3 atoms, because only this one, that is the last row, can be something that is not silicon. And then comes here. This is a sink. It's okay. And here we have a sensor, and it either drops it here or it drops it here. There is always space here because this is gonna be at most 9 columns by the time red gets here, and so this can continue indefinitely. And of course this needs to stop by the time we've done this 10 times, and this is what this counter is for. And this is a 10 counter, and I want to show it for a moment because you don't see this often, so I think it is worth it to take a moment to appreciate. Damn it, sorry, I let this input again. I want this to be clean. Here we go. So this is a 2 counter and it's easy to understand, and this is a 5 counter. So just a moment. Is this? Yeah, this is a 5 count. This is a little bit weird. What? So this counts to 2. This would count to 2. With this it counts to 3, and I guess with this it counts to 5. Okay, this is. Yeah, this checks out because without this return path, this counts to 6, and if you returned this, say here directly somehow, this is the standard 6 counter, because this is 3 and this will be 2. But because you go back path here, you toggle this an additional time because of this, and so this is 6 minus 1, 5. And this is 2, so it's 10. Nice job. Of course, this looks a little bit backwards, because you bring this all on the left to unbond it, and then bring it on the right to unbond it again. And so, if you could just go to the right, this would be faster. And this solution just goes to the right. This solution has also this, we just put it out. And let's see. By unbonding here, we can break this up easily. And then red comes here, picks up the only candidate for being gold, and it will either put it here if it's silicon, so you see, and with 2 sinks, not even 1, and an extra arrow. Man, this solution is great. Otherwise it brings it all the way down here, and it doesn't need to go all the way because it is guaranteed that this molecule is small enough. And it brings it here, and yet again, and yet again. This saves a lot of flip-flops because it only counts the time it says gold. So it is simpler to do a 4 count than to do a massively complex 10 count to do this. And so yeah, this looks pretty simple. We can check up the syncing. So this is double synced, which is a common pattern, because blue waits on red and red waits on blue. And at the last one is handled separately, because on SWI we've done everything but the last one. We hit this flip-flop here, and then this flip-flop here, and when we come back. Oh no, I mean this was I missed the interesting part, because not this one, because we have here a 4 counter for the 4 golds, but here on top we have a 3 counter, and this 3 counter is needed right here, because at this point we get this other branch in which we pick it up from the left, and so we skip an iteration. 1000. Let's go on flex column by column. And I mean, I guess he likes blue to bounce back, I guess. So blue picks the whole thing up and then brings the whole thing down, and it does it so blue holds the last atom, and it will transverse a sensor like we've already seen, and then red just kills off everything. So again, red puts it away and then comes down and kills off everything, and this iterates like this. We see that the stopping mechanism is governed by all these flip-flops here. So it's here, this is this 4 counter that counts golds, and so it's easy to know when to start a new molecule. Like this looks much more compact, aside from all these up and downs, and so it is getting a fair bit faster than we have already seen. Diverse lawyers do things, and I can already see funky counting, so we will check this up. We destroy the first column, and the red picks up a gold, and yet again these grab drops. You don't need to be grab drops, come on man. And we can see there are no sinks in the main block, so red just comes in because he knows there is a gold at each interval of 2, and this is something that you were perfectly allowed to abuse, because you know where golds are. And the sinks is only needed because blue is very late, very late. Here blue outputs a lot of stuff, and red picks them up, the regular golds, and then blue endots the last one. Now it's a pity that blue is stuck here a long time waiting for everything to clear up before it can go back. let's see red for a moment. You see there is no syncing, and it comes pick it up because it's one every shoe. Nice job. And this is much faster. We will see the solutions of this type that destroy the molecule on this place are what are the fastest solutions. And so we see Axton now, which is a similar solution but with a bond that's placed this way. And let's see. It destroys the molecule in this direction. By holding the gold, it just comes over and outputs it. And then it does the same thing. This is synced, but blue does most of the work, with red providing unbonds and blue just coming up and picking up everything. Now they exchange the work right here, because I imagine it was faster to get red to do this irregular part, and we are done. Nice job, man. You see there are a lot of unbonders, so it is there are a lot of combination and complex things you can do to unbond this thing. So 306. Now empty space. Empty space come back to the vertical arrangement, and we will see this pattern very often. So I will skip ahead a bit. This is relatively low symbols, and the cool stuff is at the end. So we're gonna watch this better right here. So red also helps. Red does the output omega, and blue does the unbonds. And red comes every time and picks up the golds because it knows they're here. And when blue picks up the last gold, rotates it so that the gold is here ready to be outputted, which is much faster than being stuck with the gold here, waiting for everything to clear up and then outputting. And this is what makes this solution much faster than the similar one we have seen earlier. About red does this loop for a bit, and then here there is no silicon here anymore, and it just escapes. So the sensor is used in place of a flip-flop counter, and it's not used to sense where gold is. 302, nice job. The British boys with another horizontal arrangement. Oh, by the way, no one used quantum tunnels because they were just not good. The metric was absurd in punishing quantum tunnels. And we see some similar work with both Waldos doing the final two golds, which gives this a leg up on the other solution of this kind. So we see it here. Red picks it up, leaves it to blue, and does it every time. But now that it triggers, it comes on this special path to pick up the last gold and get this done. So this is pretty impressive, because let's just see how the timing in this thing works. So red picks it up, brings it over, blue picks it back down, and this is sadly, as cool as it looks, it is a lot of time, because the molecule does up and down and it doesn't need to do that first up and down. And then blue comes down again and does the same thing. Then blue comes down again, and this sensor is used to make this path a little bit longer so that everything checks out, because red is very constrained and it cannot come 2 cycles sooner to get rid of this. So this looks very complicated in timing, but I mean, there was no need to make things this complicated. So we will see other solutions that do this. This is very low symbols for what it does, and we will see other solutions that use more symbols but do things in a more straightforward way, like this one. So this is very similar, but the molecule pathing looks simpler, even if the Waldo pathing is bigger and more wavy. Like we have the molecule doesn't do an unneeded back and forth, while the unbuilding is pretty much identical, and so this gets a good bit faster. And now we have Team Bag with more madness. Looks, I mean, 6 madness out of 10, I'd say. Maybe 5 madness out of 10. I've seen much worse. And we see again the same pattern. And we have a wait here by red, and when we output them both. Yeah, the initial part is done very efficiently, and right here things slow down for a bit because you have blue here, but you would like it to be here, so you need to wait for a bit. Red does stuff in the meantime, and then they both output at pretty much the same time. Nice job. 273. And as you can see, this horizontal arrangement is convenient because you unbound and you can immediately go out, but we will see there are other ways, and because this is yet another vertical bond arrangement, and this is done by having this Waldo that picks up the gold atom not be the Waldo that outputs. So the other Waldo clears up the way as this goes up. Let's see this. We don't see. Well, when we see the rotate thing to drop sooner. So let's see this in motion. Unbounds here, and the path it is getting cleared up. Nice job. Of course, to do this, you need to to get these molecules with the correct the correct selection priority, because the order the atoms are outputted depends on the order you unbond them, and because massive unbonding happens at the same time, you need to place your bonders so that this molecule is unbonded first, when this one, then this one. And you can look at this at the SpaceChem wiki. There is a detailed explanation of bonded priority and selection priority, which are both used here to great effect. 268. And now we have Darius 1 gold found, and this looks very compact, and we see he uses the same algorithm, but with blue doing a part of the way and then red doing the rest. Like this is endless especially because red can pick it up and blue does the rotation thing. Looks pretty impressive. Let's see this again. Blue unbounds, brings it here, and it goes all the way the first time. Then the second time it is blue's turn to leave it here so that red can come in 1 cycle faster. Sorry, 2 cycles faster because it is 1 place faster. And then red goes this other way to make some way for blue because blue is really packed here. And then it will pick this up and blue will do the rotation thing. And this sensor right here tells red that it is time to go into this special path to restart the thing. So this sensor is used to switch paths and not to, there is nothing that senses gold into the input. 264. And then we have GG gold, output style mastery, and this looks a good bit simpler. We see again red picks the molecule and its path gets cleared, and we see blue doing it differently this time. Instead of rotating, because it doesn't have the space, it just lops it off on the side and brings this over, while red does some part of the outputting. Let's see it better. Red does some outputting. Blue also does some outputting. This is purely wasted cycles, but he needs them to synchronize the Waldos. So, and also I guess because he needs the symbol here, so he doesn't really have a choice. So yeah, nice job, good use of this technique. You see, while this bonded arrangement has been used many times, the way the atoms escape from the mass of Earth is very different across many solutions. 254. And now we have nurture. We have nurture with a very similar solution yet again, but this has the advantage of blue pushing this molecule all the way. So there is no need for blue to regrab or do strange things. Here blue needs to lop off to waste some time because red is wasting some time on the flip-flops. and then we conclude with rotation. I am wondering if this flip-flop pair cannot be replaced with a sensor. I mean, I guess this gives some different timing, because right here it has an extra 2 cycles of latency, but it looks pretty strange. Do we really need this latency? Like, if we were to put, say, a sensor here and reduce this by 2, it may work, or it may not. Oh, people say it's needed. Okay, I believe you guys. And now we have Yellow Bunny at 5th place. And let's see, he has a very similar algorithm. So we have seen this already. It does something funky here though. Blue gets the next to last gold and it bonds here. It bonds here. This allows it to put it one on top for red, so that red can be mildly faster at doing this here. And let's see why this is needed. Oh yeah, it is because we are coming here. Oh, and Yellow Bunny himself tells me that the bond is needed for a spurious output. Let's check it out. See here. Okay, because blue is hammering output omega, and you do not want red to output this. Oh, I get it. Nice job. Beats the previous one just by 1 cycle. And now we have Sir. Yeah, and Sir suggested earlier that thing was needed, and he has the same exact pattern on his solution. And this looks very compact, and so I guess it is faster because it cuts 2 cycles of a loop somewhere. Because this thing looks very compact. So it is 1, it is 2, it is 3, and then we have blue picks up the gold right as red's stuff is starting to get outputted. Nice job. 250. And when we get into the top 3, and stuff starts getting different here. So the top 3, while solutions before had more or less the same, had some patterns, and they repeated it in many other solutions, the top 2 solutions are more unique. And this is top thoughts, and he has this much different bond arrangement and these prowled valdos all along the reactor. And what he does is that blue will run around outputting things, and he has this typical T here, which lets him debond everything over this square. So he just runs around, lops off, and this is the atom blue is holding, and so it drops it off right there. And red does the same. Now it picks it up, red unbonds, blue outputs, and red goes over here, so it puts the gold here, and it does the same with the next one. Puts the gold here, and it gets output into the red place. Let's see a moment how the first gold is handled, and we just have blue that brings a molecule all over here and gets this pair to debond it. While this is much more symbols, in a way it looks very simple. Like you just run around and do this is like unrolling loops in programming languages. So you are code the whole thing, and you just do the things one after the other. Why is this solution not first? It is not first because it does one debonding at a time. So you need one debond and one output for each thing you throw away. But if you have more bonders packed, with a single unbond you can do more unbonds, and so you save on symbols, which means you save on pathing, which means you save on time. And so we see team 89 with this solution, which comes back again to the horizontal thing, but it has this bonder here. And let's see why. Because this way they have this extra atom here, but they easily get rid of it, and then they do this. So let's check it out. They go up and destroy this section, but then they go down and destroy this other section. So it is kind of what Top did on the wall, but they are doing on this bonder cross, and this is extremely efficient because you unbond a lot of stuff with few unbond commands. And so red can easily come pick up the 2 golds when they are here. Blue is holding the last one, and then red just comes in here, lops off the last one, and it goes away. So this dual destruction, top bottom, was the key to a much faster solution. Now let's see red for a bit. Red does this 2 times, then it gets into another path, comes down here, picks this up here. Yeah, this path is very constrained because you have an atom here and you cannot do what you'd like because this rotation costs a bit of time, but then you just get here to output, so it is fine. And this is 2, which is much faster than the other one, and it is impressive how you can still save 20 cycles right here. But if you talk about impressive, you cannot expect Andy to not come in with this thing. And this, as you see, is the same bonder arrangement, and so we know he's going to do top and bottom destruction, and we see him here. And the reason this is fast is this one, because he doesn't need another Waldo to do the last 2 golds. This one is very similar to the other solution, not in Waldos but in molecule pathing, but here the molecule pathing changes, and red does everything. It lops off everything it can, and blue of course is outputting, so it's not wasting any time. And this rotation right here puts the first gold in place, and the second gold is efficiently thrown away. Amazing job. Like, this is extremely fast for what we're doing. If you think you are destroying 4 times 10 40 atoms and you're gaining 4 gold, so you are asked to destroy so 40 atoms, 4 gold, so 1 gold per 10 atoms. So you are asked to output to 200 atoms, and this is done in 205 cycles. Extremely impressive. This is nearly one output per cycle, and outputted into the right place. Amazing. So we have some fun solutions for this round, just a couple. Let's check them out. We have, Ethermate made this because the score the metric was cycles times 1 plus swaps, so this scores an humongous amount of points, and this employs an algorithm so simple even I could use it to solve this puzzle, which is to swap this over. Here we see it, we unbond it here, and we swap it over, and we swap it back if we need to output it on the bottom, and we don't swap it back but just output it if we need to output it on the top. So yeah, let's say nice. And then we have this single Waldo solution by I am asked what is the score, and I cannot say it will take a couple of days. And this is a single Waldo solution. I mean, it's not the only one. I think we had oh no, wait, this is the only one, sorry. And this does some very complex things, and I think we will watch it run, and to be honest, it picks up 4 of them, it puts them here, and then once they are here, he will sort them by passing them over this sensor. And man, this is complicated. So yeah, as we watch it, I thank all you guys for being here, and I'll see you all in the result of the next round, which will be tomorrow. Thank you.